Hello, everybody.
Yes, sir.
Just doing a sound check.
Yes, yes. It's working, sir.
Okay, perfect.
So we will let the audience in another 1 or 2 minutes. I'll just. Yeah.
Yes, sure, no problem.
Yes.
Hello, everybody.
Yeah, yes, yes. You are audible, sir.
Yes. Just doing a sound check.
Yes, yes. It's working, sir.
Is from
Yeah, yes. Yes.
You can now spatial temporal data. டாபிக் வச்சிட முடியுமா அவ்வளோ புரியலையன்றது வச்சிட முடியுமா இன்னைக்கு எதுவும் பஸ்ல சொல்ல வேணாம் அவ்வளோதான் முடிஞ்சு போச்சு
எப்படி எல்லாம் ட்ரையல் பார்த்துட்டீங்களா?
மேம் ஆமா இன்னைக்கு ஃபுல் டே அதான் பண்ணிட்டு இருந்தோம் மேம். காலையில எங்க ஹெச்ஓடி கிளாஸ் எடுத்தாரு.
Yes, Professor. Can we start? Shall we start?
Yes, ready whenever you are.
I will just give a short introduction. We will just start. Welcome, participants, for the last day of the international webinar series. So today we have our beloved professor from German. He is Dr. Peter Baumann. He is a professor in computer science and inventor and an entrepreneur. He received his PhD with the summa cum laude, highest recognition from the Darmstadt German Technical University in 1993. He formed a group on flexible service for massive multidimensional data cubes and their application in science and engineering. He has authored nearly 160 plus books, chapters, journals, and conferences, and has internationally patent works. His work on rasdaman array database system, which is a proven on pentascale spatio-temporal database and across thousands of cloud nodes, has pioneered the field of array database and data cubes. For its successful commercialization, he has founded and leads high-tech spin-off rasdaman GmbH. Rasdaman has received a series of international innovation awards. To name some, in 2019, the US TechnoConnect Award, 2019 GAN Innovator Award, and 2018 NATO Defense Innovation Challenge Award. So it's a very big work in the big data area. Since many years, our guest, Dr. Peter Baumann, is shaping Datacube standards in ISO, OGC, and the European legal framework for a common SDI inspire. In 2019, the rasdaman query language has been incorporated in ISO SQL language also. So I now request our professor to address the participants on and give us an insight on the big data cubes as a paradigm for serving big spatio-temporal database. I welcome you, sir. You can take on the stage. Thank you, sir.
Thank you very much. Thank you, Dr. Priya, for this kind introduction and also for giving me the opportunity to share with you what we are doing and what we have done in the field of what is called data cubes today. So it's my pleasure and my honor to be here virtually with Manakula Vinyagar Institute of Technology. So I would like to start actually giving you an impression of what the challenges are we are addressing by showing you a brief video.
We know our planet inside and out. At least that's what we think. After all, we monitor the Earth and its weather patterns from outer space. We measure the Earth's surface and peer into her deepest depths. In today's world of optimal hardware and intelligent software, mankind is reverting to the status of hunter and gatherers. Researchers from all over the world are compiling a vast and very valuable resource, data about our planet Earth. This data affords a new glimpse of our planet. The ongoing exploration of the world has entered the era of big data. But this development also harbors some big problems. Keeping track of the data, making sense of it, is one of the biggest challenges facing mankind today.
So this is the intro to a TV documentary that we have done some time ago together with German TV stations. It has been broadcast in Germany and France, and with permission it's uploaded on YouTube, by the way. So you can see it there, and it talks about big Earth data, as the title says. So let's see about these big data. Actually, we are focusing on a particular kind of big data that in programming is called arrays, but you find it with many other names, like, for example, gridded data or raster data, whatever. So in my university group at Jacobs University, where you get some impression here, by the way, if you want to come by as a student or researcher, you don't have to learn German. In this bubble, it's all English down to the forms of administration, because we have 110 nations and about 1,400 students. So this just on the side. I'm heading the large-scale scientific information systems research group, which is focusing on such multidimensional data services. We also have done a spin-off company for giving commercial support. And the main visible results that we have contributed so far is pioneering a new category of NoSQL databases, that is array database systems. And this is the rasdaman system that we have built and we are building. And that has led us into standardization and has been, as has been said in the introduction, we actually are shaping Datacube standards in various bodies. Okay, so let us see. We have all such many different data available, and they are so hard to serve. This is a standard task in science and engineering today. And in oil and gas industry, for example, we have the saying that there is more bytes than barrels, indicating that the main problem today is not so much transport and delivery of oil, it's getting to grips with the data. So these data very often have a spatial nature. So it's like a map, but it also can have height or depth. And by the way, it can have time. So in general, we talk about spatial temporal data that we would like to access, analyze, visualize. That means a lot of work to get them homogenized and how it's called today, analysis ready. So actually, when I talk to people in the earth sciences, I try to explain as follows. First, a disclaimer. We are a computer science group, actually coming from a database background. So we see the data world from the perspective of how can we manage data and how can we serve them in a flexible way. Okay, so we tell people, look here, you have these files, millions of satellite images, and they are so hard to digest for somebody who has no clue about remote sensing. And also you need to have coding skills. You need to be a programmer in order to write programs that walk through these files. And then you have the metadata, which can sit in the same file or in an extra file, or even encoded in the file names, as you can see here in the background. That's really not fun. What if we use something that Google Maps, for example, has done, and we build seamless maps? But we build them not only in X and Y, but actually in all dimensions. That is the idea of data cubes. We homogenize data and bring them together into one object that has X and Y extent, it has height or depth, and it has time. And time in particular is important because analysis of long time series is the killer application today. Just think about machine learning, which does exactly that. So having such an object makes it easier for humans and for machines alike to get to grips with such data. Okay, so if we now step back a little bit and see it scientifically, what exactly does it mean? Well, we have this thingy that computer scientists like to call arrays. But if you ask me, what does that mean in practice? I would say, well, it's sensor data, images, image time series, model output, like weather forecasts, for example, or general statistical data. And you find them in pretty much all domains. We are focusing on the domains of science and engineering, and there you'll find life sciences, earth sciences, space science, and of course all the engineering where we deal with kind of dynamical data in automotive, shipbuilding, and aerospace industry, and so on. So that is the world where we are moving just out of the interest that we bring along. Others deal with management data, and there you find OLAP data cubes, and you find data warehousing or fintech, so financial analysis. So this is a data structure which is very common actually. But from my perspective as a database guy, it's completely funny that database people have neglected that so long. And if we look at the data, actually, we find data categories. If we abstract away, I have picked randomly some applications and have looked at what the data types underneath are. So this is going from stock trading over climate modeling to biotaxonomies. But if we abstract away, we see that actually there are only very few such data structures that are underlying all of these different applications. So we can find common abstractions. And that means we have about 4 fundamental information categories. We have sets. Okay, in databases, this is handled by relational databases or more recently by Hadoop style systems. Hierarchies is something that is addressed, for example, by XML databases with the XQuery language. Graphs and graph databases is an exciting research area talking about ontologies in a small scale or something like Facebook graph on a large scale. Also with query languages like Cypher, for example, in systems like Neo4j. Arrays is yet another information category which stands out due to its regular organization of data. If you look at those, it becomes immediately clear you can try to simulate one category through the other, and that has been done, but it's not really efficient. and the level of service is not really good. So actually for each of those categories, it makes sense to build dedicated systems. And today, most of them, like graph and arrays, you would call likely NoSQL databases. But that's just terminology. Let's focus on arrays. So what do we want to do with them? Let me define array analytics as the efficient analysis on multidimensional arrays of a size orders of magnitude above the evaluation engine's main memory. So multidimensional, we want to think about 1, 2, 3, 4, 5, 6, 7 dimensional arrays. And we want to talk about big guys. If you can load it into RAM, you're all set. We don't need to do anything else. You can use good old MATLAB, for example, to work with it. By the way, evaluation engine, I'm talking about a server here. And if you say, but I have a server with 128 terabyte RAM, then I tell you that ECMWF has an archive of 250 petabyte of data. So yes, these arrays will be bigger than any RAM that you can afford. So it makes sense to find efficient ways of handling that and processing. Now, the essential data property is immediately clear visually. Mathematically speaking, we talk about the multidimensional Cartesian neighborhood. That means in practice, if I access the red pixel, it's immensely likely that in the next moment I will want to access its neighbors, the blue pixels. And that is something that an evaluation engine needs to take into account to be efficient. By the way, Hadoop, for example, does not know about this Cartesian neighborhood, and so it cannot be really efficient. Then as secondary criteria, we can talk about the number of dimensions. Is it 2 or 3 or 4 dimensions? What about the density or sparsity of data, and so on. When it comes to the operations, what do we want to do? Well, mathematically, it's vectors and matrices and tensors. So it's linear algebra in the end, what we want to do. Maybe a little bit more in addition, but essentially we want to do linear algebra on massive multidimensional tensors. So much about the theoretical aspect of it. This is something where we said, okay, let us see how we can give database support to that. So going beyond SQL, giving some paradigm to users that allows them to really work with that. So we have started that with that early on. And actually, there were a few attempts in addition, which typically was thesis work, but then it stopped again. But at some time, Wave came up and more groups on the planet tried to do the same thing. And meantime, array databases actually is an established research direction in my field in databases. Below there, you see an early example that we did with a German remote sensing data center. So we built a data cube out of 10,000 images, and you could do cutouts. You had a very early rudimentary web interface because web technology wasn't that good at that time, because we talk about 2001 when this was done. So spatial temporal subsetting was already shown there, but actually we want to do more than that, right? We want to analyze data. And that gets me to the vehicle that implements our ideas. It goes by the funny name of rasdaman, which stands for Raster Data Manager. The idea is very simple. SQL is a great thing. It allows you any query anytime, just not on data cubes. Okay, we said. Then actually, let's extend it. Let us establish data definitions, and let us establish operations that embed into SQL so that suddenly SQL can also be run on such data cubes. Without knowing that, it has pioneered actionable data cubes, which is documented by publications and patents. And this concept then we have underpinned with some architecture. We did it the hard way, not just an additional layer on top of some existing library or so. Actually, we did a full stack implementation to establish a massively scalable engine for big data cube analytics. Big means that today we talk about dozens of petabytes that are being served by rasdaman, and we have parallelized single queries more than 1,000-fold on Amazon. And we are doing federations, which is something I will want to show you later on. That actually has led us into standardization, but I have said that already. So let's move on. The query language in SQL style looks approximately like that. You do a table definition, and then you have the standard parts, and suddenly something called scene, that attribute actually happens to be an MD array, a multi-dimensional array, obviously with an extent of 5,000 by 5,000. Now that the system knows about that definition, it can offer operations. So we can do processing in the select clause, where we do some band ratio, like for example, the vegetation index, and we need to encode that somehow. We want to get that back as TIFF, for example. You also can use it for filtering in the server. If you put it into the where clause, like for example, looking at the average of some processed array, whether it fulfills some criterion. So suddenly you can do image analysis and signal processing in an SQL query. Actually, at the same time, it occurred to us, an effect that we didn't have in mind initially, that for the first time now you can have red and green queries in the same select statement. Green parts are metadata. Red parts are data. Traditionally, this is totally separate, and you have individual silos for the data, and you have your metadata handling, and that's separate, different methods. Now, actually, we have a common layer so that users don't need to differentiate about that any longer, but they see one uniform appearance that is queryable, regardless of how that is implemented. That concept was to the liking of the ISO guys, the standards guys. And so since last year, actually, this query language is part of the SQL standard as part 15, multidimensional arrays, or MDA. Okay, actually, you can drive that further. We have operators that allow you to do some basic linear algebra. So here's an example that does matrix multiplication in an SQL query. The red part establish a multi-dimensional array with some extent. And in the values clause, you indicate what you would compute. In this case, actually, it's an aggregation because we want to do matrix multiplication, and there you need to do a sum. So that is what the green part does. So the database can compute that for you. Another example would be a histogram. It's the same schema. You generate a new array, and then you indicate how this array gets filled with values. That is not enough yet. We are currently wrapping our minds around how can we extend that to do more general things, like, for example, machine learning as a database query. But this is still very much basic research. Let me rather show you another example. I showed you one way of embedding. Here is another one. OGC stands for Open Geospatial Consortium, and that actually is the main standardization body for geo-services and location-based stuff. They have one standard that is called WCPS for Web Coverage Processing Service. So you need to know coverage is the data structure that encompasses data cubes with a specific twist. Actually, the coverages are data cubes that know about space and time semantics. So you cannot use only Cartesian coordinates like before, but hooray, you can go into latitude, longitude, and have timestamps. So now we get a data cube analytics language that knows about these units that we like to use. By the way, as we know the semantics of space and time, we also know about what's a regular and irregular grids. And so various types of regular and irregular grids can be supported here too. Here's an example. We want to go through 3 MODIS satellite scenes, M1 to 3. And for each of them, we want to know the pixel-wise difference between red and near infrared band. Okay, so we would write something that has a slightly different syntax here. The reason being that metadata in this domain very often are in XML. So we try to come up with a syntax that embeds itself well into XQuery, and that is a flower expression, as it's called. So we have this for loop where the variable $C is bound to 3 objects. And then we compute the red minus NIR, encode that in TIFF, and ship it to the client. So the client would receive 3 TIFF files. We additionally can do filtering. If you are not interested in everything, but say just cloud-free images, we could phrase a criterion in the where clause that is evaluated on the data on the pixels, and then you may get less images actually because they get filtered out already in the server. This is again a language where you send such a string to the server and you get back some imagery. The mechanics on the arrays is identical to what we have seen with SQL NDA. It's just two differences, different syntax, and different semantics or additional semantics of space and time. Okay, so we have seen two possible languages without going too much into the concepts, but feel free to ask about that in the discussion if you are interested in that. I would move on now and just show you that in action to give you an impression. So let's go out of Windows and stop and move over. So this is something that you actually can follow yourself now or later. The URL is standards.rasdaman.com. We have built that to showcase different standards in action. So to show Datacubes standards and what you can do with them. There's a series of different demonstrations. So you can start with something one-dimensional, where you can draw diagrams and get some requests processed. The WCPS query is shown here so that you can see what has been executed on the server. You can go into two-dimensional use cases, which is what we all know from Google Maps. So you can zoom and pan, hooray. That's actually boring. Let's go three-dimensional and see what we can do here. We use NASA Whirlwind, and we load an image and wrap it around the globe, and then we slice through time. And so we see gradually how winter comes on the northern hemisphere. You can add further layers here. So we have something three-dimensional here because it is X, Y, and time. Okay, let's go 4D. In this case, we like to use Microsoft Cesium because it's better in doing what you see now, having elevation layers. So what we get is different layers that we can switch on and off. Like, for example, this here. And then you can change the footprint, of course, to get everything to your liking. So you see, we talk about queries and databases, but that doesn't mean the client has to be like this. Typically, you want to see, you want to visualize somehow. And so you would come with some clients. Okay, with that, oh, let me show you something else. Talking about eye candy. As I said, there are many, many examples that you can explore yourself. I don't want to go through them. Let me show you. Now I'm lost in my own demonstration. Hello, here it is. Come on. Okay, so the graphics people told us, did you know if you take a PNG image and in the alpha channel, that is normally used for transparency, you put in height information, then WebGL can render this in the client. Okay, we said, that's fine, we can do that. We can generate a PNG image where we take, say, Sentinel-2 satellite data, red, green, blue, into the RGB bands, and then we put a DAM, like here, into the transparency channel. And so we get this visualization in the client, and that allows us actually, again, through a query to generate the ingredients for that visualization. You see the red, green, blue, and underneath the alpha, and that computes what we see. Okay, but now let's come back. So much about such practical examples. Come back. Now, what code do we actually want to ship? I mean, there are people who say, we want to ship Python code. We just set up a server and everybody can send their Python code and we execute that on the big data. If you were an administrator of that server, would you sleep well? I wouldn't. Because as we learn in computer science in the first semester, such programming languages are Turing complete, meaning there's no way to analyze whether they're doing good stuff or bad stuff. You just don't know it. Whereas query languages tentatively have been built to be safe in evaluation. So both SQL and WCPS have this property, which means you cannot do some nasty stuff like, for example, endless loops. So some class of denial of service attacks is simply not possible. And therefore, it's a long tradition in databases to use such a language and not another one for a database interface. And it makes sense. By the way, it makes also sense because such high-level query languages are optimizable in the server. I will show you later what that means. So this is why actually for such services, declarative high-level languages have an advantage. Okay, now let's talk a little bit about the storage. Let's look under the hood for a moment. First of all, how do we store data? Well, of course, such big objects you have to partition. Everybody does that. Everybody does something that is called tiling or chunking, but it always means the same. The big arrays are cut into small arrays. Now, Paula Furtado, in her PhD thesis, actually has investigated systematically, has classified tilings from totally regular over somewhat regular to totally irregular, and has devised strategies so that the server can maintain any given structure. So, for example, if you look at that yellow cube in the middle, we might have cubelets that have all the same size and they represent an image time series, so x, y, and time. But if you know that you always want to do time series analysis, you could actually stretch your cubelets in time to make them longer. And so with one disk access, you get everything you need for answering a particular time series query. That is something that NASA has done, for example. And so it's like spaghetti for each pixel, the full history. They call that data rods. Then they found out, oops, but if now I want to do a spatial query and cut out some spatial extent, it's really bad because from every spaghetti, I need to take one pixel and then I need to reassemble my image. That is terribly inefficient. Okay, they said, obviously we need to combine some of the spaghetti into something larger, which they called data pillars. And that is exactly what you see with the yellow cube. I told them when we discussed at AGU, why actually do you hardwire a particular tiling? You can have many different tilings depending on your requirements. And so we discussed that their data pillars are just one special case out of many. What we do instead is we have extended the insert statement with a tiling clause where we offer a storage layout language where you can define strategies, for example, area of interest, that you list and tile sizes and compression and all that. So that is under control of the administrator. Users don't see that, but it's a tuning parameter for the admins. Now, some people said, oh, wait a moment, that's way too complicated. We don't need that anyway. We just want to have regular tiling. Well, let's look at OpenStreetMap. They have a similar problem, although on vector data. Downtown New York City, you may want to have a very fine grain resolution. You have many vectors, and so you want to have small tiles so that they don't grow too big in data volume. Whereas in the Southern Pacific, you maybe can have one big blue tile because there are not so many streets there as in New York City. Okay, so actually an adaptive irregular tiling does make sense, and it has been proven to give a considerable performance advantage if done right. So that is the data structure. Now, next thing, how do we put that into an architecture? In a nutshell, I told you already, it's a full stack implementation. We did the whole thing, every component optimized for arrays. At the heart, we find the rasdaman server processes, the RAS server. And this workhorse is multi-parallel, allows distributed processing without a single point of failure. Data we stored initially inside a standard database, like in PostgreSQL or Oracle or so, works, but then people said, we don't want to have an extra component. Can we omit it? So we implemented our own storage manager directly on the file system, which is about 2 times faster than PostgreSQL. And it all went fine. You import the data, you query them, and everybody was happy. No, said the big data centers, forget about that. Disk space is cheap, but not that cheap. We cannot copy data. So we had to learn something which is scary for database people. We have to process data that are not under the exclusive control of the database server. Okay, so today actually we can access any external archive. You just need to tell us the conventions. Then we register data instead of copying them. And this allows us to scale into petabytes because now we just have a little bit of extra information that we need to keep. And aside from that, we directly work on the original files. Of course, it depends on the archive structure, whether it's good for the queries or not. So for example, GeoTIFF archives are not really good for time series processing, whereas NetCDF archives are better suited because NetCDF is a multidimensional format. So there are different things to consider. Okay, so that is the overall architecture. And as I said, every component has been crafted individually for arrays, but don't worry, I'm not going to talk about that for hours and hours now. That's just one thing that people always ask me, and that is, how do you parallelize? Well, we do it like this example shows. We get a request, like this expression here, and we know the semantics of the language, so we understand, oh, the yellow part we can process immediately because we have the data. Not so, however, the orange part. We don't have the data. Fortunately, however, we do know a friend in the cloud that does have dataset B. So we simply cut out a subquery, send it over to node B, and node B processes that like any other query. For those of you who know how Hadoop works, actually, that shows a difference. In Hadoop and similar paradigms, all processing nodes perform the same task on different data. So it's like an army that is marching. Whereas here, you see that every node can do something completely different. And therefore, we achieve much higher parallelization degrees than Hadoop can ever achieve. So that is about cloud processing. At some time, we discovered, hey, wait a moment. We can send such a query also to another data center. So the blue query part would be sent as a separate query to the blue house for processing close to the data, and only the result comes back. That actually we are driving currently to the degree of moving targets, that is satellites. In a project with the European Space Agency, we have ported rasdaman on a CubeSat, and that actually makes it a Datacube engine where you can send up queries and get back results on the images that have been taken. Okay, and that is something that I would like to show you as well. To be less theoretical, I need to grab my browser window again. And let's jump over here and go to federations, where we actually see a first example. Here's a query that determines heavy rainfall risk areas. Again, it's expressed in the WCPS standard. I cannot explain the query to you. I'm not a climate scientist, but I can understand that we have precipitation data and Landsat 8 data that we use for that. We combine them. Okay, so we ship that to the German Sentinel hub, that is code DE. And now we can watch the query path here. Actually, hooray, we get a result that is displayed here in NASA Whirlwind. But that's not the interesting thing. Let's look at the query path, where actually the query went from here in northern Germany to code DE, but then they couldn't solve it. They didn't have all data. So they needed to send a subquery to Poland, Warsaw, where the other data center sits, that is Cloudflare. Oh, we can also send the query to Cloudflare, by the way, but now they have the inverse problem. They have one data set, but not the other. So they ship a subquery to code DE and we get the same result, obviously. Why is that good for users? Well, in this federation of data centers, you just send a query anywhere. You don't need to know where the data sit, and the federation nodes will find out how to optimally process that, will do it for you, and send you the result. So what you see is just distributed data fusion. How would that work today? If you want to go to somewhere, you need to find the data centers, you need to find the data there. They have different archive organizations. You need to extract and download, homogenize, and then you can do the data fusion. All of that has been done here behind the curtain. So it becomes much easier for users to work with that. That is something that we are doing routinely now with different data centers. For example, here you find a histogram of total sea ice that is computed from the data sets. So we find out that at 0 degrees centigrade, there is no ice on the oceans, whereas at minus 30 degrees, we have about 2 million tons of sea ice. And all of that can be done right now. That actually found the liking of somebody else. And our farthest member currently is Fengjia University in Taiwan. And now we send a query to them that determines vegetation forecast for northwestern of Taiwan. The query goes to Fengjia, and we have organized this query in a way that it needs to ask code DE again. And so now we get the result again in NASA Worldwind. So these are all different federations that have been built ad hoc. What we are doing currently, we unite them all in one. Let me use that one. And that is a Datacube federation, a single federation, where we have a couple of members already. You find the ones that I mentioned, plus a few more. And actually, there is a line of data providers waiting to join as well. By the way, should you have data, geodata that you want to offer, then why not join this? It's by no way European. It just happens to have started here. But we actually are thinking on planetary scale. So please do contact us if you want to get around here and participate. It's free of cost. It's totally open governance, and there is no obligation except that you should offer data, of course. Okay, let me come back. So this was where we started, doing parallel processing, doing distributed processing, and actually doing federations. So that is what we have seen already. This was just my fallback in case the demo would fail. Yes, we have done that. So let's proceed. We have some sample series here. Let me quickly skip that and just hasten to say once again, yes, we like query languages because it gives you flexibility. But we understand that many people on the planet don't like that. They prefer point and click interfaces. And so the advantage here is that there are many clients available already because we use the OGC standards. There are clients that support these standards. And so actually many different clients are possible, from very simple open layers up to high-end Python. Here are some more. Actually, standards.rasdaman.com we have inspected. Inspire.rasdaman.com is a specific demo site for the European SDI to show people how to work with such data sets. And if you want to learn more about the standards, EarthServer also has a lot of webinars, tutorials, and documents that help you immersing into these standards. Here's an outlook on a project that we do. This is a particularly exciting one because we look into machine learning. The application scenario is we want to improve rain prediction from mountainous areas. Now, rain prediction in Germany is quite good in flatland, but it's not really good when it comes to mountains because the weather just is so heterogeneous there. And so one idea of the German Weather Service and some other research centers is, hey, let's use machine learning. So have a deep learning network that tries to understand for a particular mountain area, how does rain work? This includes many different data, numerical weather forecast models, precipitation, of course, lightning, also single station measurements, and topographical data, of course. We need elevation models of the mountains. All of that together gives big data. We are talking again about petascale data altogether. And so machine learning cannot handle this really well. And this is where an array DBMS comes in. In a nutshell, machine learning provides intelligence and array DBMSs provide scalability. And that is an ongoing research project actually under the lead of Jülich Research Center in Germany. Okay, standards. I mentioned them here and there. Let me summarize briefly. OGC has a big Earth Data Standard Suite, which is the Web Coverage Service suite of standards. So you find the word coverage again. In ISO, we find in Task Committee 211 standards that actually mirror the OGC standards, just as a different naming, 19123, and here -1 and -2 for an abstract and a concrete data model. And a totally different corner of ISO is Subcommittee 32, where they do data management. And this is actually where SQL MDA is at home. Inspire, I mentioned briefly, and after some longer discussion, they got convinced that it's a good idea to align with the OGC and ISO standards, and this is what they do currently. And as we have experimented a lot with that, actually rasdaman somehow became reference implementation. Okay, now, so let me conclude what I presented. A data structure that is a little bit unusual when you think about databases. You would think about graphs and sets, tables, and the like, but not necessarily arrays. However, arrays are everywhere in science, in engineering, in business, and in further domains. So it's definitely an information category that needs flexible and scalable services. And it's a big data problem in the end. And big data means we need to ship code to the data because the data are too big to transport. We need to do analytics in the server. And that is something that we are investigating with our vehicle rasdaman. We like to use a declarative query language approach. And under the hood, you can do a lot to do optimization and distributed processing to achieve good performance. I showed you one example. There are many more techniques, and it's a wide open field actually. So there are exciting research questions actually if you're interested in that. Fortunately, we already have standards in the place, so you can use standards interfaces, and internally the system can do whatever it wants to make it fast. So, as I said, there are many questions in general, many application domains. We have also done things in human brain imaging and for cosmological simulations, but somehow the big data question was most urgent for the satellite guys, and so somehow we focused on that. And you saw the examples that I brought up using satellite and climate data. Future research, as I said, wide open. Things that particularly keep us busy currently are cost-based optimization of federated array queries. So you want to determine upfront how costly will that query be when it gets answered. And do we have alternatives to do it quicker? So you get actually a series of possible implementations for a particular query, and each of them has a price tag attached, and then you pick a cheap one and execute that one. So that is an ongoing PhD research that we have. And the other one tied to the Deep Brain project is machine learning in array databases, which is another PhD research. Okay, And that is the story that I wanted to bring to your doors, that we have some science and engineering data, which happen to be big data, and we can support them, surprisingly, with classical concepts of databases and of high-level query languages. So you got now one very particular perspective, and I would be curious about your opinions, about comments, questions. So I take a deep breath, say a big, big thank you for bearing with me, and start listening.
Thank you, Professor. I would like the audience to go for one or two questions. I think Professor can answer it. Or you can put it in the chat window.
Okay, I'm just looking into the chat. Okay, first of all, thank you very much for your kind remarks here. The PowerPoint, yes. I will send it by email afterwards so that it can be distributed. No problem. So the last one, real life application, is that a question or an observation?
Yeah.
If you want me to respond to that, please let me know.
Yes, 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 Professor. Somebody has asked for real life application. I think they might be from a different background.
Okay. So actually it is, what you saw is real life. So you saw live demos, and these are operational services that make available such data cubes to anybody who's interested. In Europe, we have the Copernicus program, and under this name, all the the Earth observation activities are grouped. There is a couple of satellites up there. Sentinel-1 is a radar satellite, Sentinel-2 hyperspectral, and then we have Sentinel-3, Sentinel-5P, etc. And these data is what we serve routinely. I had a picture here to improve the service quality, because the archives typically look like that. So you have tons of files, and essentially you have to find the files and download them. And we work on making lives easier so that people can access by just saying, I want to have Sentinel-1 of this area and this time period, and then give me some processing. Okay. Let me see. Okay. So this is feedback.
No, that's for the participants.
Right. So real life applications, as I said, we focus on Earth data. We also looked into other domains from a research perspective, but this actually is operational and supported by our spin-off company and used by agencies. So we have customers ranging from Airbus industry down to startups in the field of Earth observation services. For example, crop yield, crop analysis is what they are doing. And what else? Disaster management. And maybe I continue talking until you tell me that time is over or some other question comes up. I believe I have an example here. No, I thought so, but I don't. But I know where to find it. Okay. So another practical example was a project where we actually some other company had established a service for crop analysis for the farmers in Germany. Now, sorry, it takes a second. Okay. So it had the really inventive name of Big Picture. I apologize for that. And the idea is that you go into the fields and you analyze with the help of satellite data whether everything is okay. Okay, meaning is there a drought? Is there flood? Has there been flood? And so they actually analyze for particular areas, not just for a field as a whole, but inside the field. And that allows to place fertilizer in the right way, not too much, but also not too little. And that is something that is available to farmers, and something that actually our Ministry for Food and Agriculture liked for a completely different purposes that came by surprise. Our farmers get financial support when there are natural catastrophes. And it's interesting for the ministry to know in advance how much money they will have to reserve. So it's good to have a prediction. Will we have a bad summer? Do we need to reserve money for that? And so this time series analysis can be done for the whole of Germany in about 1 hour or so. And that has found additional interest beyond the original use case. Besides, we are also working with chemical industry to minimize, they want to give hints to the users to minimize the use. And to this end, they need to know how actually it proliferates. So if I apply some fertilizer, how does it go through groundwater? And how much does pesticides, fertilizers, how much of pollution is there for the next farmer, for example? This also has to do with legal, with law that requires these producers to give advice. And so they are highly interested in knowing what happens and giving, well, the right advice. So these are some practical applications that we do.
Yeah, thank you, Professor. I think there is no more questions in the chat window. So we can, I think there are no more questions in the chat windows. I think the participants also, many of them are from different background. Many of them find this one as a new topic. So they might be hearing it for the first time.
Yes, it's highly interdisciplinary, which makes it difficult, but very exciting. So if you are from remote sensing, from databases, from computer science in general, so hopefully there is something in it for you. And I try to give the broad overview. If you are interested in discussing further, please don't hesitate to contact me. You will get my email address as well. So yes, I see it now. Contact details, you will get them. And I will be happy to enter into conversation.
Sure, Professor. We'll get back to you. So I would like to thank you, sir, for giving us a wonderful insight on the new base for research. I think many people can explore this. Thank you, sir. Thank you for accepting our invitation and sharing your experience. We will definitely get back to you. Actually, it's just a thought-provoking session where this is a field where we have not explored much. So we will definitely get back to you. Thank you, sir.
Mm-hmm.
Thank you for your.
Thank you again for having me, and have a nice day, everybody.
Yes.
Bye-bye.
Thank you. Thank you, sir. We'll get back to you. Thank you.
Thank you, Professor.
Participant, please fill the feedback link and you can leave the meeting. Thank you all for this wonderful session. I should thank Dr. Valli for coordinating this 5-day lecture series on with international participants on various fields, and also all the participants who participated lively on this. Thank you all, and I would like to thank our principal management for supporting us in all aspects for conducting events like this. So I thank all the other coordinators who work for it. Thank you all. We will meet once again on another series. Thank you.